Paradox is a self-contradictory statement, a statement which contradicts with itself, and hence it cannot be a logical statement because we cannot assign any logical value to it. We cannot say whether a statement is true or false. So one such paradox arose in the field of mathematics, and it created a revolution. Set theory is the foundation of mathematics. Set was originally defined as a collection of well-defined objects. Now, what is collection and what is objects? If we go on searching its definition, of course, collection and objects, they are not defined they were not properly defined in the set theory. So, what is collection and what is objects? If we go on searching their definitions in dictionary, we move round and round, and so it was later decided that set cannot be defined and it should be accepted as a primitive concept. After all, what gave rise to the axiomatic set theory? It was a paradox given by Professor Bertrand Russell, a British philosopher and mathematician. Now we are going to look into this paradox and we will solve one problem on set theory. Just a minute. So we are going to discuss some set theory. My name is Bipin Musale. Now here is one puzzle. It is a seeming on the face it looks very simple. It's just playing upon words. A barber shaves all those men in his town who do not shave themselves. Does the barber shave himself? Now if the barber shaves himself, then because he shaves all those men who do not shave themselves, it gives us that barber does not shave himself. That means if the barber shaves himself, then the barber does not shave himself. And if the barber does not shave himself, then because that barber shaves all those in the town who do not shave themselves, that's why he shaves himself. So if the barber shaves himself, then he does not shave himself, and if the barber does not shave himself, then he shaves himself. So it becomes very difficult to find whether the barber shaves himself or not. Originally, set was defined as a collection of well-defined objects, and this was given by a German mathematician Georg Ferdinand Ludwig Philipp Cantor. But here, since the collection and objects, they were loose terms, they were not well-defined, set itself became a well-defined object by its elements. So what could be the objects of the set? It was not clear, it was not decided. So later on, one paradox given by Professor Bertrand Russell, it brought change in the perspective of set. Does there exist a set which belongs to itself? Now it appears very weird, but answer is also a playing upon words. Yes, the set of all sets. When we say the set of all sets, yes, this set belongs to itself. Okay. Now, although we are not able to list it properly, a set must be represented either in the roster form or in the formula method. But this set we cannot express, we cannot write, we cannot express in that form. Okay. Just as a set of all sets, it is a set which belongs to itself. So now we collect all those sets which belong to itself. So this script E is the set of all those sets which belong to itself. Naturally, the set of all sets belongs to this set script E, and hence the script E is not empty. And let script O be all those sets which do not belong to themselves. So we can easily find the sets that do not belong to themselves, a single dimension. That's not a problem. Only the problem was with the set which belong to itself, and so far we could find only one, that set of all sets. No other example it was possible to find. Now, the question is, does this set script O, does it belong to itself? Does this belong to itself? What about set O itself? Now, if O belongs to itself, then because of the nature of the elements of the set O, all those elements of the set O, they do not belong to themselves. Therefore, O does not belong to itself, O. Okay? So, if O belongs to itself, it will satisfy the property of all the elements of O, and O will not belong to itself. Okay, then we ask the question, does O does not belong to itself? Then, if O does not belong to itself, then because by the very nature of the nature of the elements of O will belong to itself. So if O does not belong to O, then O belongs to O. So what we get is O belongs to O and O does not belong to O. They are equivalent statements. That means they will have same logical value, but O belongs to O and O does not belong to O are negations of each other. So two statements which are just negations of each other, they cannot have same logical value. So what we have got is that our assumption that there exists a set which belongs to itself, it leads to a contradiction. What is a contradiction? A contradiction is a statement that is always false. It cannot be true. So our assumption of existence of set belonging to itself, it must be false. Because in order that this statement, there exists A such that A belongs to A implies a contradiction. If this statement is to be true, the consequent, and we know that this consequent is false, the antecedent also must be false. So there exists A belongs to A, this statement must be false. But see, A is a well-defined element because it is defined by its own elements. So now, this definition, set as a collection of well-defined objects, had to be discarded. But mind you, still in many practical situations, this definition comes very handy, and many books use this definition also. So this paradox was given by Professor Bertrand Russell. And why this happened? Why this paradox arose? Why this definition had to be discarded? Because there was no restrictions on what could be the elements of a set. There was absolutely anything well defined that could form the element of a set. So there were no restrictions. So there were unrestricted freedom was enjoyed while defining a set. So this leads to the maxim that unrestricted freedom leads to downfall. Now we will see one problem. Now this is many times a symbol is misused in mathematics. So here on the left hand side it is complement. This bar overhead means complement of the set. So we are having a complement of A union B intersection. The another set which is complement of A intersection B. So complement of A union B intersection, complement of A intersection B. And on the right hand side we have A union B complement intersected with A intersection B complement and its complement. So we start with the left hand side. Suppose X is an element of the left hand side, the set on the left hand side. Now what does this mean? X belongs to complement of some set. This simply means that X does not belong to that set. So X belongs to complement of A union B intersection. Complement of A union B means X does not belong to the set under that the exteriormost bar. Now this means what? X does not belong to A union B and X does not belong to A intersection B bar. X does not belong to intersection of two sets. This means X does not belong to A union B, or X does not belong to A intersection B bar. The negation of a conjunction is the disjunction of negations according to the De Morgan's law. Now, if this is true, X does not belong to union of A and B. This means again X does not belong to A and X does not belong to B. Same here, application of the De Morgan's law, that if X does not belong to union means X does not belong to any of the two. Or now here X does not belong to the complement of some set means X belong to that set. Now if this is true, what will happen? We just expand this. X belongs to A intersection B. If X belongs to intersection B, only when X belongs to both of them. So this is conjunction disjuncted with another conjunction. Now we make use of distributive law. This X belongs to A, this we disjunct with the left side bracket, and then this one X belongs to B, this we disjunct with the left side bracket. Now again we will have to distribute this. So if this is true, what we get is this, that you distribute this X belong to A on both of these. So we will get X does not belong to A, or X belongs to A, and X does not belong to B, or X belongs to A. And same here we do, X does not belong to A, or X belongs to B, and X does not belong to B, or X belongs to B. Now see these two things, X does not belong to A, or X belongs to A, P or not P. Such thing is always true. This is a tautology. Here also P or not P, X does not belong to B, or X belongs to B. Such a statement is of the form P or not P, and it is a tautology. Such type of statement is always true. So we just replace that with, say, true, a tautology. True and another statement, and this statement and true. We replace this by just true. Now we are having that any statement conjuncted with a tautology, it's equivalent to what? It's equivalent to the statement itself, because this conjunction will be true or false depending upon this very statement. X does not belong to B, or X belongs to A. So this entire thing is equivalent to only this part. Just like 2 into 1 is 2. So if this belongs to this, this part is equivalent to this part, and similarly this part is equivalent to this part. So we get this conjunction of these two disjunctions. Now what we get is X does not belong to B, or X belongs to A, and X does not belong to A, or X does not belong to B complement. Just we replace B by B complement. It now appears some manipulation. So X does not belong to B bar, or X belongs to A, and X does not belong to A intersection B bar. Because here again, yes, the negation of conjunction, or here disjunction of negations is the negation of conjunction. It is a De Morgan's law. So finally we get X belongs to this A union B bar, and X belongs to complement of this, and that is X belongs to intersection of this, which is the right hand side. So thus, so far we have proved that left hand side, if X belongs to left hand side, then X belongs to right hand side, that is left hand side is the subset of the right hand side. But for proving equality, we require the other way inclusion also. So we start, retrace this argument, implication arguments. So x belongs to A union B. X belongs to right hand side. If this is true, then because the right hand side is a intersection of two sets, so x belongs to both of these sets. That's why if this is true, then this will be true. Now if this is true, x belongs to this set and x belongs to this set. Now what is this? X belongs to complement of something means x does not belong to that set. And x belongs to union of two sets means x belongs to at least one of the two sets. That's why if this statement is true, then this statement is also true. Now what about this? Here we are having x does not belong to intersection. X does not belong to intersection. That means we have negation of what is intersection here. X, either x A intersection B bar means either x belongs to A or x belongs to B bar. Now here we have negation of conjunction is the disjunction of negations here, and here just we write this is x belongs to complement of B means x does not belong to B. So that's why this is equivalent to this and this part is equivalent to this part. Therefore, conjunction of this part is this implies conjunction of this part. So that's why this will imply this. Now, x does not belong to B or x belongs to A, and x does not belong to A or x does not belong to B bar. Now this x does not belong to B bar, we write this as x belongs to B, and here this we keep as it is. So we get this is equivalent to this. Now what we do? This part we just conjunct with the tautology, because anything conjuncted with tautology is equivalent to itself. And similarly this part we conjunct with a tautology. So that's why this part is, this will imply this again. And now what we will do? This tautology, we will give a concrete example. We will replace that tautology with a concrete example, that is x does not belong to A or x belongs to A, and another tautology, this we replace by concrete true statement, x does not belong to B or x belongs to B. Although it seems some manipulation, but that we can't help. And now if this is true, suppose x does not belong to A or x does not belong to A, x does not belong to A or x belongs to A, and x does not belong to B or x belongs to A. So now we can take out x belongs to A outside by distributive law like this, and same thing here, we take out x belongs to B outside by making use of distributive law, and so we get if this entire statement will imply this statement. Similarly, what about this? Now x does not belong to A and x does not belong to B, or x does not belong to A and x does not belong to B here. So this we take out. This is a common factor. So this is by distributive law again. This implies this. Now what happens to this? X does not belong to A and x does not belong to B, or x belongs to A and x belongs to B. That means x belongs to intersection of these two sets. X belongs to intersection of these sets. This is equivalent to this, and this is the same statement. That's why this will imply this. Now, if let us look at this statement, x does not belong to A and x does not belong to B, or x belongs to A intersection B. If X belongs to some set, then X will not belong to its complement. And this is negation of conjunction of two negations. Conjunction of two negations is a negation of disjunction. So this is equivalent to this and this is equal to this. Therefore, conjunction of these two statements is equivalent. Disjunction of these two statements implies disjunction of these two statements. Now, what about this? X does not belong to A union B, or X does not belong to A intersection B complement. So here, because X does not belong to this or X does not belong to this, that is conjunction of negations is negation of disjunction of negations is negation of conjunction. So that's why we get this statement. And what about this? X does not belong to this means what? X belongs to complement of this set. X belongs to complement of this set, which is nothing but a left hand side. And thus we have proved that the set on the right hand side is contained in the set on the left hand side. And that's why what we get is the double implication of these two statements. That first implies the second, and for right hand side implies the second, left hand side and left hand side also implies. So what we get is this equality of two sets. Thank you so much. Thank you for watching.